the end of chem activity number 15, there are a number of exercises for you to attempt, and I highly encourage you to give these a try. Right now, I'm going to talk you through one of the exercises. You'll see that the idea here is we're trying to determine the most basic atom in a particular compound. I've written out the compound 3 times because there are 3 atoms in this compound, each of which could accept a proton. The molecule actually looks rather complex in that there appears to be both an ester group as well as an amide group. The idea here is that we can't actually decide which is the most basic atom simply by looking at the conjugate base, but rather we need to draw the charged species, which would be, of course, the conjugate acid. So I'm going to first of all show the conjugate acid in each of these cases. I encourage you to stop the video and write these down yourself. So indeed, you can see that the conjugate acid is the one that bears the positive charge. In order to decide which is the most basic atom, we need to decide which particular atom with the positive charge is the most stabilized. To facilitate talking about these different conjugate acids, I'm going to label them as conjugate acid 1, 2, and 3. Just like working with negatively charged conjugate bases and their relative stabilities, we will apply the Areo template or the Areo approach. First of all, looking at the atom effect, looking at the particular atom that bears the charge. In conjugate acid 1, we see that it's an oxygen that bears a positive charge. In conjugate acid number 2, we see that it's the nitrogen that bears the positive charge. And in looking at conjugate acid number 3, we see initially that it's an oxygen that bears a positive charge. Now I'm getting ahead of myself a little bit, but I'm anticipating that conjugate acid number 3 is going to have some stabilization by resonance. I can see that there's an allelic lone pair on the nitrogen, and that we could find a resonance form where the nitrogen would bear a positive charge. There would be a pi bond between the nitrogen and the carbon, and the oxygen would no longer have a positive charge. Or actually on the other side here, I can consider another resonance form where in fact the oxygen on the left would have a positive charge. So in terms of the atom effect, I can write both a nitrogen with a positive charge and an oxygen with a positive charge. If the question asked you to actually write out the various resonance forms to justify your explanation, of course we would write out 2 resonance forms consistent with what the arrows are showing here. In terms of the resonance column, conjugate acids 1 and 2 do not have any other resonance form. So I'll just put an X here, but of course I'll put a tick mark with conjugate acid number 3. In terms of induction, we have a positive charge on a relatively electronegative atom. Next to these positive charges, we have 2 other electronegative atoms attached to carbons. There's definitely going to be pulling of electron density along the sigma bonds towards these electronegative atoms from the carbon, thereby making the carbon electron deficient and that actually destabilizing the positive charged oxygen or nitrogen. So if anything, in terms of induction, there will be destabilization by induction. And that will apply to all of these. So I'll put these dashed lines to indicate that. Finally, in terms of orbital effect, normally when we're dealing with positive charge, we don't really need to consider the orbital effect. Now initially, we might have thought that the conjugate acid number 2 is the most stabilized and therefore the nitrogen is the most basic atom. But we can see after having explored the idea of resonance stabilization, conjugate acid number 3 has positive charges both on oxygen as well as nitrogen. In addition, it has stabilization by resonance. Therefore, conjugate acid number 3 is the most stabilized, and the most basic atom is this carbonyl oxygen. Experimental data confirms this, and this will be important when we're considering various mechanisms, especially where one of the steps involves a protonation step and there's some choice between which particular atom will get protonated. Usually it will be the carbonyl oxygen that gets protonated. I hope that you have found this example to be helpful in considering how to approach the other questions in this exercise.